Okay, so the next session is about annotating your data. So I think, okay, maybe first this is our team. So my supervisor, Sebastian Böcker, and my work colleagues, Markus, Martin, and not on the photo, Fleming and Wei. So it's super easy to remember. And yeah, so just to give an overview, we had first these pre-processing steps where you did the feature detection and you got your feature table. And you did GPS for spectral library search. That's usually the first thing you do for annotating your data. But as you already noticed, you can only annotate a very small amount of data because spectral libraries are basically incomplete. And so that's where we now continue. Basically, you want to annotate all the offer data points, all the offer components you have measured, for which we don't have any spectral library hit. And yeah, from then you can do the statistics. It's a session tomorrow, or visualization and data exploration. I mean, that's basically what you do with GPS and Cytoscape, and what Daniel is then showing you with Cytoscape. You can also do pre-processing in SIRIUS, so instead of MC-MINE. I just showed to you, basically you can just drag and drop all your MCML files into the SIRIUS UI, and then it will do the pre-processing, and basically it's doing the same steps as MC-MINE. So you have feature detection, isotope picking, adduct annotation, also alignments. It doesn't has any interaction and any parameters, and some of you might think that's a good thing, but this also means you cannot adapt the pre-processing to your data. So you can drag and drop it, and it gives you some results back, and you have to live with them. And so if you really want to make best out of your data, then you might rather use MC-MINE, because it allows you to really set the parameters adapted to your data, set the right noise level, and so on. While SIRIUS will just try to figure out itself which would be good parameters. This might work if you do it really bad, but it's definitely worse than a human who has really knowledge about his data. Another, I wouldn't say problem, but another consequence of the SIRIUS preprocessing is that it's somehow targeted. So it's still for untargeted metabolomics, but it's targeted in a way that SIRIUS is first going over all your NSMS spectra and then picking the peak, which is corresponding to the MSMS. So if you have basically here your peaks, and you have MSMS here, then SIRIUS will just pick the single peak here, and it will ignore the other peaks. If they don't have MSMS, they don't exist for SIRIUS. And the reason is that SIRIUS is really for annotating the data for which you have MSMS. And if you use MC-MINE, then you can also do statistics on data points for which you don't have MSMS. So this advantage you have to consider. For this workshop, we will just use the MC-MINE data, which you already pre-processed. And I think yesterday we already had how to export it for SIRIUS. Just in short, you have your feature list methods, export feature list, and then the SIRIUS user finger ID. And basically you can keep the default parameters. What's important is don't click on renumber IDs, because otherwise the names in SIRIUS will be different than the feature names in MC-MINE. So you want to keep the same names, so don't check this box. And everything else doesn't really matter. You can merge the MSMS if you want, that's totally okay, but you don't have to. If you don't do that, the file will be a bit larger and SIRIUS will merge them internally later. And that's how these exported files look like. So it's an MGF file. You can open it in any text editor. And basically it just adds a few additional fields for SIRIUS to import the data in the right way. And the important thing is the feature ID, so that SIRIUS knows which MS1 and MS2 spectra belong to which row in your feature table, and also the ionization, which was detected by MC-MINE maybe. Okay, so let's go on with the feature annotation in SIRIUS. And it's basically consists of these 4 steps. So it's basically here the molecular formula annotation. That's the first step, annotating molecular formulas on all your MSMS. then molecular fingerprint prediction with structured database search and compound classification. And so nowadays, most modern instruments are high res and high mass accuracy. So sometimes people ask, why is molecular formula even a difficult problem? If I have high mass accuracy, sub ppm, it should be easy. And this is here just to show you it isn't easy. Like just one example of a molecular formula here. This is basically this peak here, and this is a window of 2 millidalton. And every gray line here is basically an alternative molecular formula, which has a similar mass like this molecular formula. And I just show you a few examples here. I mean, these are all molecular formulas, which doesn't look that bad. I mean, some look a bit strange, like this one with 10 nitrogens. But I mean, if you don't, I mean, some of them could be chemically feasible. And they don't only differ in the fourth location of decimal points. So it's super similar to this mass. And so even with high mass accuracy, there's always some kind of ambiguity. And slide for that? No. Okay. And so the way SIRIUS tries to annotate the data is first using isotope pattern analysis, and second with fragmentation pattern analysis. And yeah, the important thing is that SIRIUS is really considering all molecular formulas that are possible. And it is not using database search, which means if you have some super novel compound in your data and it's not contained in any database, then the molecular formula annotation can still be done with SIRIUS, although it's not contained in any database. I think that's a huge advantage. And so the first thing basically SIRIUS is doing in the isotope pattern analysis is trying to figure out what are the elements of the molecular formula of your compound. And many elements have a very specific isotope pattern, like chlorine, for example, you see here, has a very large third peak, or has a very large second peak. Bromine has also a very large third peak, but much larger than chlorine, and so on. And so basically, if your molecular formula contains one of these halogens, then the isotope pattern will look very different from the normal C13 isotope pattern you might are used to. And so basically, the first thing SIRIUS is doing is trying to figure out from the isotope pattern what are the elements in your molecular formula, and it can do that for all the elements which have a special isotope pattern. Of course, there are also elements which don't have an isotope pattern, like fluorine or iodine, and for them, SIRIUS cannot figure out the elements from the molecular formula. Yeah.
Yesterday, you showed us an NTMSS there was this option with these isotopes. How does this relate to what I do in NTMSS where I use this option and not you showed it yesterday?
It's a good question. I'm not sure. The thing is, MC- is using that to pick the isotope pattern. And in the worst case, if it contains chlorine, then MC- might not pick the isotope pattern correctly, I think.
Yeah, I can add to that. Like, that's why the MGF is different. Like, SIRIUS actually uses the MS1 data to more extent than the GPS. So we export the raw MS1 spectra, or attenuated spectra, and then we also export the detected isotope pattern from MC-MINE. But I think SIRIUS just uses then the MS1.
So it doesn't matter whether I've gotten this optional
thing
in MC-MINE.
Yeah. Like those optional things were actually more like when we would do more annotation in MC-MINE, which we do, like spectral library matching. We could then also look at the isotope pattern that matches to the formula that we determined for our ions. Yeah, so we could in MC-MINE use this isotope pattern.
Okay.
And this is unrelated.
Okay. Thanks.
Okay, and then basically the next step would be it enumerates over all possible molecular formulas that have the desired mass, and then simulate how the isotope pattern would look like for this molecular formula. And then it basically just makes a comparison of the measured data with the simulated isotope pattern. And there's some statistical model, maximum likelihood model, which assigns a score how good the isotope pattern matches your data. And Then the second part is basically the fragmentation kit analysis, which computes a fragmentation tree. And this is just, you know, a scheme of a fragmentation tree. Basically, every node of a fragmentation tree corresponds to one peak in your spectrum, and it assigns a molecular formula to this peak. While every edge of this tree, so these connections, corresponds to a mass delta in your spectrum. And yeah, both is annotated. And so what SIRIUS is doing is, again, going over all possible molecular formulas, which for each fragment peak, and then for all possible connections between all these formulas, and trying to figure out what would be the best explanations. In the end, it searches for one tree that somehow, by some statistical model, best explains your data. And that's how the tree looks like in practice. So if here a spectrum, and basically peaks are colored green if they are explained by some node in the tree. And hopefully most peaks are green, so most peaks are explained. And you have for each peak a molecular formula explanation, and you have these mass delta explanations. One thing here is, so some people here might wonder, why do we have so many fragmentations? Like in a QTOF, in a CID cell, you don't have 10 fragmentations after each other property. And so you shouldn't interpret these edges in a tree as a fragmentation reaction in the CID cell. It's not the same. So it's not that we say, first there's an H2O going off, then another H2O, and then CO2. It's really more like the molecule fragments in a way, and these are the annotations for the mass deltas, and these annotations correspond to functional groups or substructures in the molecule. That's the idea, and that's working usually quite well. To see, for example, these H2O losses and CO losses often corresponds to hydroxy groups, for example, and like some mass deltas like these carbohydrogen often corresponds to some steroid substructure or terpenoid substructure, and so on. And yeah, or here these C4H4 are often some fatty acid chains which cleave off. And yeah, maybe we just try it out in the software. So I have here the MGF file. Just drag and drop it into the software, and then it loads all the compounds, which hopefully doesn't take so much time. So basically here you have the list of all compounds, the features you have picked in MC-MINE, which have an MSMS. You can also sort them. I think by default they are sorted just in the order they appear in the MGF file, which usually should be the order of the retention time, but you can also by right click say order it by retention time, or order it by name or by mass. Yeah, and here you basically can inspect the spectra, so the MS1 spectrum and the MS2 spectrum. And here the LCMS tab basically doesn't work if you import from MC-MINE, because SIRIUS doesn't know about your raw files. You just imported the MGF file, which only contains the spectra, but no information about the mass trace and so on. So this tab would be only available if you import the raw data directly by SIRIUS. So now you can basically click on compute. Here's the compute all button, but we won't use it now because if you would really compute all the 2,500 compounds, it might take 1 to 2 hours, I guess. So instead, I will just select some compounds and just compute them. We have right click and then on compute. And here's the compute dialog with the several steps we will discuss today. And now we just discussed the first step, SIRIUS. And so you also have a lot of parameters, but in general, you can just keep them as they are and just click on compute. I will just go over the most important one. So here's the instrument, which can be QTOF, Orbitrev, FTI, ICR. The thing is, the instrument is just what's your expected mass accuracy. So if I say it's Orbitrev, which I think our data is Orbitrev, it just says, okay, the mass accuracy is probably much better. But because we have DOM data, I would just leave it to QTOF because the data is super messy. So the it doesn't really matter which instrument you use, it's just what's your feeling of the mass accuracy. It's more like orbit trap, or is it more like a Q-tip?
Mass error should be sub 5.
You think so? Okay. Then do orbit trap. Okay. And here's the formula view, the formula database search. Okay, that's maybe I wait. Yeah.
When you just said that all the permutations were wrong, right?
Yep.
So if you, from the data you get from MZ9, if you only want to do the subset of that, you edit like the MDF, or how would you sort?
I mean, if you only want to analyze a few compounds, I would just look for the MC and RT value and look here, where's the compound, right click on it, compute, and it will just compute a single compound.
More like 1,000 out of 3,000, and so it's like if it would take a long time to.
I mean, it's not really taking a long time, to be honest. Like 1 hour is not a problem. It's just, it would be a problem if you do it now here in the workshop, you know. Like just let it run overnight. If you think about how much time it needs to acquire the data, I think the computation time is quite low.
So yeah, that's fine. I didn't know how long. But yeah.
And yeah, so I said, let's do it orbit trap. And here's basically, if you really want to search in a molecular formula database, you can select the database here, like the bio database. Yeah. Okay. So everyone is basically trying to open the menu currently. And just select some compounds here, doesn't matter which one. Then selecting orbit trap. And here we don't want to select the molecular formula database because we want to do de novo. But you could if you want. If you don't, if you say, okay, I have a, I don't know, human sample, and I'm very confident that every compound there is in the molecular formula database, then you could, for example, select HMDB here, and then it will only consider formulas from HMDB. And this might be, in fact, sometimes useful if you expect that your data contains rare elements. Like, as I said, stuff like fluorine cannot be inferred from the isotope pattern. And that's basically the menu here. Here you can select which elements are enabled. And by default, we just have CHNOPS plus everything that gets an isotope pattern. And this means that fluorine, for example, is set to 0, so we don't allow fluorine. You can, if you say, okay, my data might contain fluorine, you can just make the slider here to some value, like allow 10 fluorine or allow an infinite number of fluorine. But this might really increase the time to compute the data by a lot. And it also might decrease the quality of the annotations, because particular fluorine is really nasty. It has a very low mass, it has no isotope pattern, and it fits everywhere. So you might get 10 times or 100 times as many molecular formula candidates in a software that has a really hard time to figure out which of them is the right one. So I would keep it 0 usually, and if you really know, okay, my data contains fluorine or it contains iodine or something like this, then just search in the molecular formula database. And we will click on known because we don't want to search molecular formula database. And yeah, you can keep everything else as it is. And then click on compute. So the way SIRIUS is working is that it's distinguished between adducts that stick on your peaks and adducts that can change. And like stuff like NH3, for example, can cleave off. And so your peaks are NH3 adduct, but then another peak is an H+ adduct, for example. And that's why we only consider at this point sodium adducts, potassium adducts, and protonation. This are only ionizations which are considered at this point, and only in the structure identification data we will consider offer adducts, because for the tree it doesn't make a big difference. And usually you can just enable all three of them, so potassium, protonation, and sodium, because they will occur in your data. I mean, even if protonation is the most common one, you will also see sodium, and you will also see potassium sometimes. And yeah, that's how then the results might look like. So you have here your MS2 spectra, and on the right side the fragmentation tree, and here the result table in the formula tab. And basically, this is the score, which consists of the isotope score and the tree score. And as you can see, the isotope score is 0 here everywhere. And that's because we only have a single isotope peak. So that's your measured data, your measured MS1 spectrum. And as it was picked by MC Mayen, and this is the theoretical one. And you see if this molecular formula would have this isotope pattern, but we only have a single peak, so the score is 0. And this is also typical for DOM data, because most of your compounds there are so low abundant that you don't see an isotope pattern for every compound there. So we have a lot of compounds here which don't have an isotope pattern. Yeah.
So you have the SIRIUS score, and then even if you have a 0 isotope score, it marches to 100%.
Yeah. So
the gravity would be more. Can you explain a bit how it?
So I hate the percentage points here, but or any other one thinks it's a good idea. I don't know. So it's basically a probability, like it takes all scores into account and then renormalize and then give you a probability for the tree. But the probability shouldn't be interpreted like a real probability that it's 100% the right formula. So I would be a bit careful. But it's just an, I don't know, many people don't like these scores, so we show them a probability. But it's basically the tree score plus the isotope score, and then a renormalization into a probability. Like the scores in SIRIUS are all already log probabilities, because it's a probabilistic model behind that. So you can always transform them to real probability values. And so this is the best tree, and it explains 53 of 58 peaks. And it explains 95% of the intensity. And here you see stats about the mass error and ppm. So the median mass error is basically just the median over all mass errors in your peaks. And the median absolute mass error is basically taking first the absolute of each mass error and then taking median, which means this value here, if it's close to 0, this means your data is very calibrated, so there's no systematic mass shift in there. While this column here is more telling you what's the mass deviation in your data, in the sense of how large are the errors. Okay, so we also have tabs just for the fragmentation tree, where you can look into the tree in more detail. And here you have the formula candidates, and basically, as you see, this one has a quite high score, so probably it's also the correct one. And yeah, that's basically the molecular formula annotation first part. And none of them has an isotope pattern. That's a bit unfortunate.
Ignore single mass traces, or like just ignore features that don't have a monotropic.
No, I think we don't have that. We haven't that. In general, I have the feeling currently that the SIRIUS preprocessing is more sensitive for isotope patterns. So if I use the SIRIUS preprocessing, I get more isotope peaks here. So I think the setting in MC Mayen might not be perfect, the parameters to select all the isotope peaks, but I just used the MC Mayen results basically I got, so I didn't preprocess data myself. But yeah.
Really high, so we have like very low MS2 spectra.
like the software says something, oh, okay, maybe you are fragmentation tree type. Because it can happen.
I mean, you see it in the data, and it's definitely a problem for us. So if you have a higher fragmentation energy, you see only peaks in the low mass range. And this will be a problem. The other way is you have a too low energy, then you just see the precursor peak. It's also a problem. So for the software, it would be perfect if you have peaks distributed around the mass range. That's a perfect thing. Like here, that's perfect MS2.
Yeah.
And we don't have something like a warning for the user, please remeasure your data, but I agree it would be a good idea. The ACMS tab has something like this. If I go into my, says yet it's the right slides. So, this was the one I expected. Like what you see here is basically that the number of molecular formulas is increasing. It's a logarithmic scale, so it looks like an exponential increase with the mass. So for 1,000 Dalton, you already have around 10,000 molecular formula candidates per peak. So it's really a challenging problem. It's not really exponential, it's a polynomial, but it's a high degree polynomial. Here basically you see it. So if you have the ACMS preprocessing used, then you get some quality traffic light basically that tell you here how good is your MSMS. And I don't think that's currently takes the distribution of peaks into account, but it would be definitely a good idea to do that, to also to tell the user, all your peaks are just in a low mass range, please lower your collision energy. For us, the iterative thing would be just to use several collision energies or use a ramped collision energy. Of course, this then also lowers sensitivity, so many users don't like that, but then you usually get the best results out of your MSMS analysis.
I can ask a question. Now as like electron-based fragmentation methods start to become a thing with like the xenotrophs.
Okay.
Is there any
so it's EI or?
Yeah, it's EI, but also other, I think it allows different modi. So
okay.
Are there any ideas of SIRIUS to develop towards electron-based fragmentation?
So it's a hard ionization or soft ionization, because that's, I think
it's hard.
Okay.
To get more fragments, right?
Yeah, but in particular, you don't see the precursor anymore. If there's no
it's MSMS, so you still have the precursor.
But ionization happens before the MSMS.
No, it's fragmentation.
Okay, fragmentation. Okay. So I mean, I wouldn't say it's a problem for SIRIUS, and because maybe you would have to update the statistical model, but probably even not that. So our statistical model was trained on, I think, 3,000 compounds, which was a lot 10 years ago. But nowadays, I mean, you have 30,000, 40,000 compounds available in public libraries. And just for fun, I retrained our model and find out nothing changed, which is quite cool. So the model is really robust. And so I could imagine it will also work on different fragmentation methods, as long as they high mass accuracy, and as long as you don't have crazy stuff like there's no precursor in your data and stuff like that. So like, for example, GC is not possible with SIRIUS, because in GC, you don't have a precursor. In many cases, you have to somehow come up, where's the precursor in my data. You have, of course, chimerics everywhere. You have unit mass usually. So this kind of data comes with its own challenges. If you have ACMS data and has a different fragmentation method, I would say just try it and check if the results look good. If they are not looking good, you might be able to improve the statistical model by retraining on a few compounds. That's maybe also possible.
What would be the library size that you would?
I would say 1,000 would be good. Yeah.
What the library size and the retraining of the
But I mean, we don't have a separate model for positive and negative ion mode. And this tells a lot, like, because positive and negative look different, but they are not so different that we would need a different model. So for SIRIUS, it doesn't really matter. We will see the next step with CSI Finger ID, which is a machine learning model. it's really a problem. There you really need training data, and you really need that your test data is made in or is processed in the same way as the training data. So one part of the molecular formula annotation I skipped so far, which is the zodiac part. So basically, if you look into your molecular networks, I mean, Daniel showed you the domoic acids network, and there you, for example, saw that the mass status are always this methylation, and all the compounds are looking similar. And this usually, if you have molecular network and zoom in, that's usually the case. So you have your nodes with very similar structures and very similar molecular formulas. Obviously, because the networks are built with the cosine similarity, so two nodes are next to each other if the spectra are very similar. And so far, we basically processed each node independently. So we have processed each spectrum on its own. And the idea of Zodiac is basically to process your whole network together, basically. And so the general idea is, if you have two compounds which have similar spectra, then probably the annotation for these spectra is also the same. Like if they share all these peaks, then probably all these peaks should have the same molecular formula annotation. While if SIRIUS is doing an error, like it's, let's say it's would annotate this compound from and this compound correct. It's here. This compound correct and this compound from, then the annotations of the tree would be very different. Like in this example, there are only two fragments which are the same and only one loss which is the same. While if both compounds are annotated in the correct way and with the correct molecular formula, then both trees are super similar. And yeah, this is basically the assumption behind Zodiac. It's just after you compute your fragmentation trees, goes again over all fragmentation trees and check if two spectra are similar or the trees should be similar. If this is not the case, then there's some error. And then it tries to re-rank the trees and get a molecular form or the tree which is more consistent on the top. And so this can be quite powerful, in particular if you have biological samples where you know that all your compounds come from some biosynthetic pathway and there are all these intermediates maybe, so they should be similar. Then it's a good idea to run Zodiac. Also, if you have a lot of compounds, so even a DOM sample, if you have several thousand compounds, it's a good idea to run Zodiac to improve the annotations a bit. And I skipped this part. The reason is that usually SIRIUS is compared to just searching the MZ value in a database, you usually get a very low identification rate. With SIRIUS, usually can expect 70 to 90% identification rate of the molecular formula. If you use reference database like NIST, which have many collision energies, you get usually in the area of 90% correct identifications. However, this is really dependent on the masses. Like you see here, for small molecules, we have almost 100% correct annotations, and then it goes down very quickly. And for large molecules with H1 Dalton, we are just to 20% correct identification rate. So only for 20% of the super large compounds, we get the molecular formula right. And the nice thing is that Zodiac, so this network analysis, can really improve on this area. Like if you have a lot of super large compounds, then it's super important to also run Zodiac, so this network analysis, because here you see, for example, this is the error which is done by SIRIUS, like 50% up from, and this is the error done by Zodiac on this data set. So for large compounds, it can correct many errors which are done by SIRIUS. And so if you want to do Zodiac, you just have to additionally to SIRIUS, or you can also do it afterwards, click on this button. And in this case, it will directly tell me a warning because the number of compounds might be too low. Here are a lot of parameters. You can ignore all the parameters. You just have to, additionally to SIRIUS, click on this button, and then it will also run this network analysis and improve the molecular formula annotations a bit. And I won't do this now. You should do this now too, because the problem with that is you have to do it on the complete data set. So you have to compute the complete data set, which a set takes probably 1 or 2 hours. So we will just skip for the demo the zodiac step. But the difference would be then just that you get here additional column zodiac score, which might then be a little bit different than the SIRIUS score. So the formulas might be a little bit re-ranked. Okay, so this is basically the molecular formula notation. And the next step I think we do after a break would be then the structure database and compound classification. Yep.
So I'm using SIRIUS and the database I'm using not always. I noticed even though I use a lot of files that have known compounds, that if I use the bio database or something similar, I'm getting sometimes quite weird formulas compared to the normal.
I mean, that makes sense somehow. So basically, first thing is if you search in PubChem, then it will consider all stuff there. And there's also stuff like, which is not organic. And so sometimes super strange formulas pop up. And the other thing is, I mean, that's a general problem. If you search in a database, you always get a hit. And sometimes this hit might be super bad, but it still gets a hit, it's still at a score, and it still has a rank. Like it might be rank 1, but it's still a bad hit. And I think a really good technique to check that is always check your fragmentation trees and the number of explained peaks and intensity. Because this really tells you if your annotation makes sense. I would say you should have around 70% explained intensity. Then it's a good explained spectrum. However, for DOM data, you might get worse results just because what happens here a lot is that you have some isobaric compounds and they both go through the isolation window and are fragmented together. And then SIRIUS only explains hopefully one of them and not the other one. But the other one will still contribute to the number of peaks. And it's not explained, so the number of explained peaks goes a bit down. But that's normal in DOM. Yeah.
Do you like circle standard? Isotopic standard?
We don't support them, but we could, I mean, so basically, I'm not sure if you mean to use isop labeling to
Isotopic labels.
on all compounds or on standards, or on standards.
Yeah, would that mess up the isotopic pattern?
Yeah, but I mean, you can just, as the thing in the iso pattern is also, if it's really messed up, then SIRIUS ignores the iso pattern, because this just sometimes happens. Like if you pick the from pattern, or if there's 2 compounds next to each other in one Dalton window, and you pick both as an isotope pattern, then it's also messed up. So in this case, SIRIUS just stop. If it sees, okay, the iso pattern is mixed, is totally messed up for every molecular formula, it ignores them. So usually it shouldn't make your analysis going completely wrong. But I mean, this is just, you know, one of these features I think I could implement quite quickly if somebody asked. It's just, there was never a reason to implement standards, isotopic label standards. Yeah.
So a question about the SIRIUS score.
Mm-hmm.
Now the top one here, in your case, is 100%.
Mm-hmm.
But the 3 scores of the others
Yeah.
are quite okay. The explained peaks are quite okay. And explained intensity is also quite okay of the others. But they get 0%.
So the reason is that this score are log probabilities or log odd probabilities. So you would have to get probabilities out of that. You have to renormalize them and then take the exponential function. And then the exponential function is the critical part here. So basically, if a tree has score 200 and another tree has score 199, they have one score difference. But this means due to the exponential function, one tree is twice as likely as the other one. But I wouldn't trust the probabilities at all. Like, I mean, in this case, 206 and 176 is a big difference. But if you have a tree like 206 and another one has scored 200, I would say they are both good. So I wouldn't say the one is 100%, the other one is 0.
The SIRIUS score is like, it's 100% and it's most.
I mean, it's 100%.
Unlikely that the rest is a possibility.
I mean, as it's renormalized, so it assumes that all scores sum up to 100%. So there will be always 100% here, or at least the sum of all compounds has to be always 100%. So and I said, if the score is just a little bit different, like 5 or 6 in the difference, then it's already from an exponential function a lot, like it's already 100 times more likely. So that's normal. But usually, I don't know, I would just look at the rank in the end, because you don't want to really, if you analyze 2000 compounds, you don't want to go over each compound individually. So in the end, just hope that the software picks the right one on place 1. And later, if we do the structure database search, we can also correct some errors by SIRIUS, because the structure database search then really checks maybe the second one or third one is also correct, and we also check them. So as user, usually don't check individually all the compounds. And there you can just say, okay, if it's 100% and 1% or 10%, that's okay. And 0% is probably not the right answer. Okay, then how long is the break?
Yeah, let's take a break for, I don't know, 10 minutes or 15 minutes.
So a few people told me that they have connection problems. Problem is that there are all kind of strange things going on people's laptops. So sometimes the antivirus scanner, sometimes the department laptops don't allow you to use some software. So the best thing is always write an email to the SIRIUS support, because my colleague gets thousands of such emails, and sometimes he already know the problem and can directly help you. In other cases, it's then some days of writing emails and sending screenshots, but that's just as it is. Okay, so we had in the first step the molecular formula annotation, and now comes basically, we want to know something about the structures of the compounds and not only the formulas. And so historically, I mean, you already had MS library search in GNPS. And the problem is with this, you usually can only annotate 6% to 10% of your data points. And historically, the first software tool which allows you to do more was Metrc, which came to with the idea of searching in structure databases like Coconut or HMTB or even PubChem, and then try to figure out which structure there could fit to your mass spectrum. And nowadays, there are quite a lot of such methods. So there's CFMID, there's MS Finder, and CSI Finger ID, Magma. And yeah, we want to talk about CSI Finger ID, and which is the software within SIRIUS which does the structure annotation. So you don't have to download a separate software, it's just basically part of SIRIUS. And the idea is basically the same, searching an MS spectrum in a structure database. And the problem which CSI Finger ID or its predecessor Finger ID wanted to solve was basically, if I have a spectrum, can I give the user the structure corresponding to the spectrum? And Markus Heinon was the guy who worked on Finger ID, and he was machine learning. So he tried to solve this problem using machine learning, but yeah, came to the conclusion it's a really, really hard problem. And so what bioinformaticians usually do if a problem is really hard is just changing the problem instead of solving it. That's much easier. So what they then did was, instead of predicting a structure, predicting a molecular fingerprint. And the molecular fingerprint is a vector where each position corresponds to a certain structural pattern. Like here, just exemplary, like this position corresponds to this group, this position corresponds to, I think, benzorin, and so on. So you have for each position in your vector some structure. And if you have a molecular structure, you can compute such a fingerprint just by going over each position and then checking, is this structure contained in your molecular structure? If yes, then write a 1 in there, otherwise write a 0 in there. So you get basically a 1-0 string. And such molecular fingerprints are in use quite a lot and since a long time, because molecular database are usually using them to compare molecules. So if you go on PubChem, for example, and there's often a tab like similar molecules and suggesting you offer molecules which look similar to your molecule, then they use usually fingerprints to find similar molecules. So it's data structure used in chem informatics a lot. And so he came up with the idea of predicting such a fingerprint from a mass spectrum. And the nice thing is, first, this is a much easier problem. And second, if you have such a fingerprint, then you can search the structure with the fingerprint in a database. And so why is this a simple problem? So basically, a fingerprint consists of many bits, and each bit corresponds to a substructure. So let's just start with the first substructure in fingerprint, which let's say is in benzoyl. And then basically you want to answer, given this mass spectrum, does it contain a benzoyl ring? And so it's a quite simple yes/no binary decision problem. And these are things which are done in machine learning since centuries. So it's a well-defined problem. And you can do any kind of machine learning method like random forest, neural networks, or in this case, support vector machines to solving that. And the idea is you give the machine first thousands of spectra containing a benzoyl ring and thousands of spectra that do not contain a benzoyl ring. And the machine learner is figuring out, okay, which peaks in my spectra are indicators of a benzoyl ring and which peaks are not indicators of a benzoyl ring. And if you then give him a new spectrum, it then searches for these patterns and says, yeah, this is a spectrum containing a benzoyl ring or not. And after I've done this with benzoyl ring, you can do that with 5,000 other structures. And then you just have, let's say, 5,000 machine learning models that you run on your data, and then you get this molecular fingerprint back. And as I said, the first method doing that was Finger ID by Markus Heinun, and these are Finger IDs and basically a successor methods, which is using a bit more advanced machine learning methods. Instead of kernel SVMs, we use deep multiple kernel learning. And instead of just looking at the spectrum, we also look at the fragmentation trees. And I always give some example why this is so cool. So these are just two structures, which as you see are super similar. And these are the spectra. And this is just a nice example where the spectra don't share any peaks. So the cosine similarity of these two spectra is 0. And crazily also the modified cosine, so the measure which is used in GNPS, which is a bit more smart than just cosine, I think this one is also almost 0 for these two components. So it's super challenging. And if you look at the trees, you see that the trees don't share peaks, but they share a lot of losses. And I mean, this whole subtree here is also visible here. And as I said, so these losses basically reflect certain functional groups and so on. So if the machine learner is not only looking at the spectrum, at the peaks and the losses, but also, you know, at the structure of the trees, he might figure out, okay, that these two structures might be similar. So that's basically the idea by using trees and spectra together, give you more information for the machine learner. And yeah, that worked out quite well. So there are these flying contests every few years. So we call it CASMI, Competitive Assessment of Small Molecule Identification, where people basically get data which is unlabeled, and then they try to figure out what's the compounds in there. And then there's a high score, which methods performs best. And so since this, I think ID was released, it more or less always win these contests. More or less means that in 2016, it was just on rank 2, but rank 1 was just the method by the same developers who tried a different machine learning model. So it was basically still the best performing machine learning type of method. And yeah, the last one was this year actually by Oliver Fien. And there also we got, I think, around 30% of the structures correct on a really, really challenging data set where even many compounds were not even contained in structured databases. So that was quite nice. And yeah, here's the overview basically. So you have your MSM spectrum as input. You predict the molecular fingerprint. So for each of these substructures, you get a probability that this structure is contained in your molecule. And then you go in, for example, PubChem, or I wouldn't even use PubChem in practice. You would use HMDB or Coconut, so some biodatabase. There you get a lot of structure candidates with the same mass as your precursor. And then you just compare the fingerprint of these structures with your predicted fingerprint. and get some score how well they agree with each other, and then you can rank the candidates based on the score. Yeah, so it's just an outlook for what we do next. So basically, the cool thing on fingerprints is it starts as a method to search in structured databases. Like you can use it to search a mass spectrum in structured database. However, the prediction of the fingerprint itself is not using any database. So this means you get, even if your compound is again null and it's not contained in any database, we already had SIRIUS, which can still find a molecular formula for it, hopefully. And also CSI Finger ID can still predict a molecular fingerprint for it, even if it's not contained in a database. So you get some knowledge out of the compound, even if you don't know the exact structure. And with this knowledge, then you can basically do several analysis like compound class prediction or even de novo structure prediction. Although that's quite advanced and still very experimental. And so let's go in the software again. Where is it? Low resolution, or I don't find it anymore. Okay, so we have here our, what was the key command to hide the control? It's K? H. So thanks. Basically, we can again double click on the compounds, and we already computed the tree. So this time we can, this is basically the fingerprint prediction, predict fingerprints. And here we can search the fingerprint in structured database. And these two steps are separated such that you can say, okay, if I don't want to use any database because I know my compound is not contained in any database, then you can just leave that out. But usually you would just click on both of them. So predict the fingerprint and search in a database. Here are the adducts, which it should be should consider. Again, adducts should be usually detected in the MS1 analysis, and if that have worked, then you don't have to click on anything here. So if it not worked, then you should fix the MS1 analysis, like, because adducts are really nasty thing. You don't want to consider any adducts here, which are not found in the MS1. So just leave all these things as they are. And here you can select the database you want to search in. And there are a lot of databases. However, biodatabase is basically a collection of our databases which contain biocompounds. So if you click on that one, then you have everything in there, like HMDB, Coconut, BioSig, Knapsack, and so on. And you would only click on another one if you really know, okay, I have a human sample, so I only want to consider HMDB, then you would choose HMDB. But usually it's not necessary because biodatabases are quite small, like they contain around 500,000 compounds. So you just can search in a complete biodatabase. And the alternative would be searching in PubChem. And then things get difficult because PubChem contains over 50 million of compounds. So this is then really 100 times as many candidates. And if you do that, expect that you get much more from annotations than if you just search in the biodatabase. So usually in biological samples, you will just search in biodatabases. And the reason is that PubChem contains often derivatives or modifications of biocompounds. Like you have, let's say, cocaine, and then you have a variant of it where just one partial group is moved to the left or to the right. And it's super hard for MS to distinguish these two candidates. And so searching PubChem will just make more confusion than it helps. So predict fingerprints, search database, select biodatabase. I mean, it's the default. And then we can click on compute. And now we can look here. Oh, damn it. What's happened? I can, but this shouldn't be a problem actually. Now rerun SIRIUS. but always says that the server connection failed for some reason. But we have an internet connection. Does this work for you? Okay.
How's the web services connection?
Claim it's super slow also, so maybe there's some internet connection issue. Yeah, but Zoom is working, so. The problem is both need internet connection. Actually, they are not. I mean, the main reason is that the machine learning model is trained on real data, and it's also trained on data like NIST, which is commercially available. So we cannot give out a model without giving out NIST, you know. Yeah, it's like in GNPS, you know, when you do spectral library research in GNPS, as long as you search in public libraries, that's fine. But if you search in NIST, things get a bit more complicated with the licenses. So that's why we keep also fingerprint prediction online. Yeah, we seem to have problems with the connection. We can try to restart the software and hope that this goes away, but I don't think so. Oh, let's see. I mean, there are two alternatives. If it doesn't work, we can use my laptop, and I also have a complete run basically, so we can also use that one. I just didn't want to put that on the USB stick.
I mean, you could just log in on your laptop to Zoom and then just
yeah.
share your screen and then you just like that.
Ah, that's sounds like good one. Oh, let's see. No, failed. No. And again, checking connection. Okay, then let's try this one. So I need to zoom. Yeah. Das kannst du auf Switch erstellen. Guck mal, das geht. Webbrowser. Und dann haben wir ich mache dich kurz zum Presenter.
Ich muss das Screen sharen können und nimmst Blatt hier mit, dann können wir noch weiter über das Mikrofon laufen lassen.
Also. Das Bild meinst du?
Ja, du kannst einfach hier davor stellen.
Perfekt. So, I mean, that's data set basically where I already processed all the data. And after clicking on compute all and predicting fingerprints, you now have these new tabs here. And this basically the structure candidates you get from the biodatabases. And so here's the ranking list. And every square here is basically one molecular structure, which is contained in the structure. You can also click on them. And then it highlights basically the corresponding structure. And if the square is blue, then it's predicted by the method. If it's red, then it's not predicted. Like this one actually is quite bad. Like as you can see, most of the structures are not predicted. And let's see if we have some nice compounds.
So this one you discard.
I mean, we come to this later. Which one you should? I mean, for example, this is perfect. So it's cocaine. Oh no. You have perfect predictions. Everything is blue, and there's also when you right-click on the compound and say highlight matching substructure, it also tells you in blue which part of the molecule is predicted and which part is unsure. Like, take let's say this one. You see, it would reject this part of the structure, but say, okay, this upper part is correct, but here is something strange. And here you see the databases in which this compound is found. And you can usually also click on the databases. So if you click on HMDB, it should open in a browser directly the entry for this compound. And basically there are two scores. So you see the score here and the score here a little bit hidden. This is the correct score, which is used by Caesar Finger ID, and it's again some probabilistic score, some log score, and which is hard to interpret. This is a very easy to interpret score, but it's not good for ranking. So this is the score we show to the user, such that he gets some impression how good the data is. This is a score which is used to decide which structure is rank 1 or rank 2 and so on. And this one is easy to interpret because it tells you it's tiny moto of the fingerprint to the structure fingerprint. So you can think of it like how similar is the fingerprint to the structure fingerprint. If it's 100%, then both fingerprints are the same. If it's, let's say, here 80%, this means that around 20% of the entries are different in both fingerprints. And you can also look into the fingerprints directly in this fingerprint tab here. And here you see basically the complete list of all fingerprints. Now that's, I think it's around 5,000 bits. So it's quite a lot. What you usually do if you want to inspect that is you say, I'm only interested in fingerprints which are predicted with a probability of, let's say, 50%. So set the slider here. And then you say, order them by the number of atoms, such that the large structures, which are maybe easier to interpret, comes first. And then you can look into the bits, and basically on the lower side here, it shows you examples how this fingerprint looks like. like it says you that this substructure is contained in there. And the mean thing is that sometimes rings are not, doesn't matter if there's a ring or not. So in this case, for example, you see the fingerprint just consists of this sequence of atoms, and it's not important if they are connected into a ring or not. That's why we show several examples of this substructure. It predicts these kind of substructure and so on. So you can basically go through these bits here. It's always a good idea if, for example, the structure is not contained in the database. You might get some idea how the structure looks like just by browsing here through the substructure elements which should be contained in the fingerprint. Another thing which is important is this is just the candidate list for this molecular formula. And in cases where you are not sure about the formula, because maybe the top two formulas are both really good, you might you can switch to the candidate list of another formula by clicking on it. However, for performance reason, it only computes the candidate lists if they are good. Like in this case, the second one has such a low score in comparison to the first one. It doesn't compute the fingerprints for them. So find here, for example, we have several candidates which have the same score. This always happens if there's an adduct. Like here, the trees are basically the same. It's just which adduct is used for these trees. And so can switch between these different adducts just by clicking on the formula, and then you see the candidate list. In this case, for example, you see that for these two adducts, there's not a single candidate in the biodatabase. And this one has a candidate, but with a really low score. Okay, so that's actually a nice example of a compound which is a lipid. And so for some lipid classes, SIRIUS has lipid rules implemented just basically as a backup. So in this case, it's monoacylglycerolphosphocholine. So for phosphocholenes, for example, it's well known how they fragment. So additional to SIRIUS, we also have a lipid fragmenter which checks is the spectrum corresponding to a lipid, and then it applies these lipid fragmentation rules. And basically this just tells you this compound here is APC16, so it's a phosphocholine with one fatty acid chain of length 16. And just in case there is no database hit here. And also it reminds you that for lipids, you don't know the double bound locations. So in this case, it doesn't have any double bonds, but let's say it would have a double bound, then you shouldn't trust the database hit too much, because double bound could be somewhere else and it wouldn't change anything on the spectrum. They would look indistinguishable. But yeah, in case it's phosphocholine, for example, you would also get here this annotation. And I think you can click on it and it goes to lipid maps. Yeah. And then you get the lipid maps entries for that. Okay. All right. Maybe we should do that on the. Pause share. And share screen. And we want screen.
So do you want to look what is?
Just put it there. You can put your comment. You can put it there.
Okay, so I already unmuted myself. Nobody mutes me. Okay, so I said this fingerprint prediction step is don't using any database, which means you get information from from it, even if the compound is contained in the database. However, this information is not really accessible. As we have seen, the fingerprints are not easy to interpret. And so one thing to change that was Canopus, which is basically a tool that predicts compound classes from the predicted fingerprint. So idea is you have your spectrum, you predict the fingerprint, and then from this fingerprint, we predict to which compound class it belongs. And it doesn't work. H, yeah. And one thing which is important is, so we use basically two ontologies for compound classes. One is classifier, the other one is the natural product classifier. And for classifier, there's basically the way they define compound classes is over structural elements. And it means that a single compound does not have a single compound class, but many. Like here's an example of a compound, and these are all the compound classes it belongs to. So it belongs to a secondary alcohol because it has this OH group here. It's a valine derivative because it contains this valine substructure here, and so on. It's also for that an alpha amino acid. So that's just important to keep in mind that there's not one compound class, but many one per compound, which makes it always a bit difficult to visualize this in the end. And the NPC classifier is a bit easier because it just has one compound class per compound, and it's more also more natural product related compound classes. However, it doesn't work so well like classifier. So we do both, and usually classifier works a little bit better. But for visualization, the NPC is quite nice because it only assigns a single compound class per compound. And so what we want to do, I mean, I can also show this in action in a few seconds, is you have your molecular network, as Daniel showed you. And basically here, it's not the DOM data sets, it was another one, but you see basically in black all the unknowns, and in orange or red all the database hits, not database hits, database hits in the sense of spectral library hits. And as you see, most of the stuff is still unknown. And what's really a problem is that there are a lot of clusters of unknowns, like where you complete molecular family, all nodes are unknown, don't have a single hit, so you cannot infer the annotations basically. And so the idea is basically with Canopus to annotate everything there. And as usual, if you annotate everything, it doesn't have to be correct, but you get a full picture. That's the idea. And then you can just zoom in and look in your molecular network and have everything colored by if it's an amino acid or a steroid or tritopenoid and so on. And here, this is just an example where you have such a molecular network with all these annotations, like this part are isoflavonoids, here you have flavonoids and terpene glucosides and so on. And for each node, basically, we have these annotation, which is a classifier consists of this ontology, like the kingdom is organic compounds, the superclass is phenylpropanoids, the class is flavonoids, the subclass is flavonoid glucosides, and then it goes on. And then you have what is called additional classes. That's what I showed you, that the compound does not have a single one, but many additional classes, basically. And yeah, then you can do, for example, statistical analysis. I just will jump over that because that's important for the workshop, I think, but it's more an outlook. Basic idea is that you do analysis or statistics on the compound class level. Like in this case, we, I think, analyzed germ-free mice and specific pathogen-free mice, so mice which is treated with antibiotics, is the blue one here. And the orange one is basically normal mice. And then you compare how the distribution of compound classes changes in several origins between these two conditions. And yeah, and then you can just make statistics, compute p-values, and find interesting results, hopefully, like here that bile acids are abundant in the normal mice, but low abundant in the antibiotic-treated mice, for example. And yeah, that works on a compound class level. It means you don't need the annotations of the compounds themselves. And here's just another example where we compared plant samples from different plant species, and then we just compared the distribution of the compound classes and found, for example, that different species has a very different distribution of diterpenoids and tritterpenoids, for example. And then you can, for example, cluster them with that. And I will just again show it in action. But that's basically then the last thing here, the Canopus button, and usually you just enable all these buttons and click on compute, and it makes a complete analysis. And yeah, Canopus then will compute the compound classes, which is then the compound class tab here. And so you see here the what we call main class. The problem is that the main class is sometimes not so clear what of all these compound classes a compound can has is the main class. So it's basically defined as the largest structural pattern, but sometimes it's, if a compound, for example, is an amino acid and a fatty amide, then it's not clear which of both appears as the main class. And here are all the alternative classes then. And here you see the natural product classifier. And I said it's a bit easier. It has a pathway, a superclass, and a class. So the pathway is the idea is the biosynthetic pathway which produces this natural product. And then you see here it's a glycosylphosphocholine and belongs to the fatty acid pathway. And here's basically the complete list of all common class together with their probability. But usually I think this view is easier. And again, you can usually click on these classes, and it will again open in the browser the corresponding entry in the classifier, which explains you what it is and also gives you structure examples for this compound class. And let's see, we can just open the cytoscape. Daniel will later show you how to get all this information basically in the molecular networks. I just have done this already at home, and I will just show you how it looks like in the end. Because in SIRIUS, you always look at the single compounds and look at their statistics and so on. Of course, the idea is later to get the complete picture and look at the molecular networks and at annotations here. Quite a lot of data it has to read. Yeah, I mean, in this case, I just put all the data in there, like Canopus and Caesar finger ID. So yeah, I can come to the cosmic score in a few seconds. So basically, this is our data. Oh, that's really out. And the diamonds are basically, I think, spectral library hits. So and the coloring of the nodes is based on the compound class. So, and I think I used the natural product classifier compound class because it's easier to visualize that. And then you can zoom in and you see the structure prediction by Caesar finger ID. And let's check. Compound class here for this one is fatty acids, octanoids. I think I also found the oleic acid somewhere here. There was a huge cluster of the compound class kainoid, which I like a lot. Don't know where it is actually, but where you find a lot of domoic acid derivatives, basically. But there you can now go in, and this, for example, are alkaloids, the blue ones. And usually you also see that one molecular family is then usually consists of one compound class most time, or at least a few compound classes which are related to each other. So we see that they usually cluster quite nice. Not always full. Like in this case, for example, well, I think that's just the NPC classifier, which sometimes it's not clear to which common class it belongs, but they are all here. Probably something like amino acid alkaloids or something like this. So it's, for example, this is tryptophan alkaloid, obviously is also amino acid somehow. So the coloring is not always clear in such cases. If it's now an amino acid or belongs to alkaloids, that's what I mean. It's always the difficult thing. There's no unique answer to that usually. So that's why you sometimes have these inconsistencies in the coloring. But if you look then really in the compound class, it makes sense. Like these are all alkaloids, peptide alkaloids, nicotinic acid alkaloids, tryptophan alkaloids. So the compound class are quite consistent between in this cluster. And yeah, the point is that you basically get annotations for all the nodes and not just for the ones for which you have spectral hybrids. I said the diamonds are the spectral hybrids. If you look here, there are not many of them. So most of the annotations are without spectral hybrid research actually. But it also means that you don't really know if they are true or not. That's always a problem. If it's a machine learning derived annotation, then there's always some error rate. And I said the error rate is usually around 50% to 70%. So you can think of half of these annotations are wrong. But it doesn't mean that they're completely wrong. It could also be that the right answer is similar to the structure, but not exactly the structure. And that's why sometimes just thinking about common class instead of structures makes totally sense, because even if the structure might not be perfectly correct, it's very likely that the common class is correct. There we have much higher identification rates, basically. So the common class are most time correct, I would say. And so if you annotate or evaluate your data, basically you should keep in mind that if it's somehow said it's this structure, and it can be always from, you never really know that. But the compound class is much more reliable. That's basically the idea. And so the last part then basically is about cosmic, and that's exactly the topic. How can we somehow assess if our annotations are correct? And that's what I talked about a few minutes ago. If you search in this database, you always get a hit, and sometimes it's wrong, sometimes it's correct. And as a user, I would just look at the scores in the beginning. So if a compound has a very high score, or in this case here, this is the CID score, this is the matching score. If they are both high, then this is a good indication that it's the correct hit. Another thing you can look at is difference. So if the first hit has a medium score, but all the other hits have really, really low scores, then it might be also an indication that this is the correct hit. There's still a chance that the correct hit is not contained in the list because it's not contained in your database. But in general, I would say if the top hit has a really good medium score and all of the scores are low, then might be also the correct hit. On the other hand, sometimes you have stuff like this. If you look at the scores here, the top two compounds have almost the same score. And one of them is rank 1, one of them is rank 2, but it's more or less random, I would say. And that's always a bad thing. If they both must have the same score, you don't know which of them is the correct one. Another example, of course, is if a compound has a low score, then you would put also not trust in. And the question is now, can we somehow automate that? And that's then the tool Cosmic, which takes into account the scores, the score differences, which compound hits you get in PubChem, but also like how good is the quality of your MSMS data, how good is your fragmentation tree, and how well annotated is the fingerprint. And with all this information together, it tries to predict somehow, is this a good hit or is it a bad annotation? And it gives you then a score, a probability score again, between 0 and 100%. And high probability means it's more likely a correct annotation. And that's basically then what you see in the software on the right. So you always see for each compound here the Cosmic score, and you can also sort by the Cosmic score. And this will then basically give the best annotations on top. And I mean, we just see that, so we scroll through these annotations. They are sometimes have super high scores, like here, so they are probably correct. From laptop thing. And sometimes they have not so high scores, but there are no alternatives. And sometimes they have meteor scores, but the second best hit has really low scores. So it's also an indication. And Cosmic in the end makes a number out of that, such that you can sort it, and then you can scroll basically from top to bottom what's through the best hits. And if I would now scroll down, or is it from laptop? Then I see here now the bad hits. And if I say bad hits, I mean, the thing is often they are just not so easy to distinguish, because I mean, this one doesn't look that bad. But quite often the two hits are almost the same, and then it's just not clear which of both is the correct one. So it gets a low confidence score. What the confidence score is not considering currently is taxonomic information, but that's always a good thing for you to decide if something is correct or not. So you can, for example, if it's a knapsack, click on the knapsack, if it works. And knapsack always has information about the origin of the species for this compound. So in this case, it's fungi. There's also another database which is called Lotus, which is quite large actually, which is not yet in here, but it will be in here soon. And with that, basically, you can also, if you know my samples come from tomato, you can, for these compounds, sometimes also click on these knapsack or Lotus links and get information. Yes, this is really a compound from tomato, and it's then always strong indication it's the correct compound. Another thing you can do is the Substructure Rotation Tip. I almost forget that because it's quite new. And this basically tries to assign or fragment the compound, the candidate compound in silico, and assign fragments to the peaks. And you can see here the spectrum, the MSMS spectrum. In basically, peaks are black if they are not annotated by SIRIUS. They are blue if they are annotated by SIRIUS, but not by in silico fragmentation. And they are violet if they are annotated by both. If I click on the violet peaks, then I see, for example, this peak can be explained by cutting these two edges here. This peak can be explained by cutting this edge and this edge, and so on. Let's take a nicer compound, higher confidence score. Here you see these green ones are green or blue, sorry. These green peaks, green means there is no explanation for this peak, and that's always quite bad. So I would always don't trust them too much. Here we have a lipid, for example, and we have here the OH group cleaving off the, how is it called? Forget it. This functional group here. And yeah, or here the CO bond And I think that's also a nice way of inspecting your data. So if you already have a structural hit and you're not sure if it's correct or not, you can look into this substructure annotation view and then just check the peaks to which substructure of a compound belong they, and what's the bounds I have to cut to get these substructures. And if I only have to cut a few bones, and if these bones are also CO or CN bones, this is always a good indication that the annotation makes sense. However, what's also quite interesting here is always, if we look at suboptimal hits, most of their peaks can also be explained. And that's just a discussion I had with Daniel, I think, many years ago, where he said, why not just use in silico fragmentation? It's so easy. You just have to cut some bones and then you can explain everything and with the right compound and nothing with the from compound. But unfortunately, that's not the case. So if you use the from compound like here, I mean, it's super low scores, really likely from, you can still explain most of the peaks. So this in silico fragmentation is not for annotating the data in the first place. It's really more like I annotated it with CSI and want to know if the annotation makes sense. So then I use the in silico fragmentation basically. Okay, I think that's about SIRIUS and how to use it. I would continue quickly with how to get the SIRIUS results into a cytoscape. But maybe first, if you have questions about the software, we can also go over that yet.
I was it again that sometimes you did not find structure because I have like 100% score, but then I have no structure.
The 100% score, I think, is the SIRIUS score, isn't it? The 100% score, I think, is the SIRIUS score. In the formula view, isn't it?
It is, yeah, zero isotope. The structure score is 100%, but then there's no.
No, the structures is tree scores 100%, I guess. I mean, it is, so the isotope score is 0 because there are no isotopes here.
Structure sometimes you have these crying emoticons.
Yeah.
Why was that again?
Because there is no structure in the database with this mass or with this molecular formula. And that's what it says. So you can rerun it with PubChem. So actually, it's quite easy. Just click on search database. This time we select PubChem, or you can also just click on all. And then it gives you much more candidate hits. Then now it got a different confidence score, and I don't find it anymore. Yeah.
The computing takes quite a bit of time, right? And so you want to save it.
Oh yeah, right. So basically by default it's saved in the temp.
And then you have this option of one is serious project and the other one is something else. I never got the logic of
So by default it just stores the whole thing in a temp directory of your operating system, which means if you restart the computer, it's gone. Yeah, so usually you just want a SIRIUS project directory, which is just a directory of all the results and compounds and so on. The other thing is just a zipped file. That's all. It just zips the directory, and it just, if you rename the ending in .sirius, but it's just a zip file. Just if you want one file per project and not a directory. But I think you never need that. It was historically more in the beginning. We didn't zip anything in the directory, so it was quite large. Now we zip most results in the subdirectories, and it doesn't matter anymore if you use project director of workspace, both is similar size in the end, so you can just keep the project directory, and then let's see, desktop. I mean, in this case, I already saved it. Summer school DOM, and if I open that, you basically has the one directory for each compound, and the compound names in SIRIUS are a bit might be a bit confusing because you get a prefix, which is the first number, which is an internal number for SIRIUS, and then you get the name of the compound, which is then the whatever comes out of MC-MINE usually. And I think in MC-MINE we take the file name of the MC-MINE project and then the feature ID. That's the last number in this case. So if you import from MC-MINE, then the last number here is the MC-MINE feature ID. And if you open this directory, you get then the spectrum is in this file. Windows. Open with more apps. Sublime. And yeah, that's basically the spectrum. And these are then the structure candidate lists. And you can open it with Excel with all this information. Basically, you will have in the UI, you have here as tab separated file, basically, with the scores and in which database they are found and so on. And you have the same for the molecular formulas. And all the other things here are basically zipped directories where all the trees are in there and all the fingerprints, the predicted ones. So basically you can get all these information. You can also get the fingerprints if you want them for some offer tool, for example. It's all just zip directories.
Most of the files, they contain the name of the feature, then like the SIRIUS name, and then I always find it difficult to.
Yeah, I know. The thing is,
like the Canopus output file doesn't have any.
I know. I mean, I showed how to do that currently, but it's definitely something you just can change because it's just an artifact that these are two separate softwares, and it's not always. You should talk more with each other. So it's just that MC-MINE feature ID might not be unique, so we always add a unique number beforehand to ensure it's unique. Because in theory, you could, for example, process two MC-MINE projects and then load both together into SIRIUS, and then you have an overlap in the ideas. So that's why SIRIUS always adds the name of this MC-MINE project and the unique ID beforehand. And but in practice, you never need that. In practice, you have one MC-MINE project and one SIRIUS project, and then it would be nice if it's a bit easier. Yes, I fully agree to that. So it's just something we have to do. It's not a problem. I mean, the directory structure will always have this unique ID because that's just necessary. But if you go, for example, here into the Canopus compound summary, just open that with Excel. Strange that Microsoft is not even asking me if I want to open that in Excel.
You run feature-based networking, then predict the formulas and structures, and then integrate them, like feature-based networking with MC-MINE.
Yeah, totally. I mean, there is here a button for which is FMBN export. So if you make the pre-processing SIRIUS, you could export it to GNPS if you want that. But if you did the pre-processing MC-MINE, you can do the GNPS stuff from MC-MINE and then just pre-integrate the information. I mean, that's what we will do now, I guess. So
Maybe pretty short output files.
Yeah, so basically, this is, for example, the Canopus output file. Oh, no, it's the structure output file.
all the information about the feature.
And it is in there. So it's basically, here's the ID. And I said the last part of the ID is the feature ID of MCMine. All you have to do is get this into a separate column. And we can just, it's just a patch of a few minutes to do that in SIRIUS directly. I just didn't want to do that 2 days before the summer school, and then all of you have to download the new software. But I guess it's in 1 or 2 weeks, it's just in there. But until then, you just have to basically make here a function in Excel, and I think it's a category text function.
You can also just like split the column. We'll do that again together for satisfaction.
Ah, perfect. Text nach, I think, is that. It's also in German, sorry. So probably it's not that helpful for you at all. But basically you would now say, take this column here and split it on the lower bar. And because there are several lower bars here, we're only interested in the last one. So 1, 2, 3, 4, 5, 6. And then we get the number out, right? And then we just do that for everything. And if you then store that in a file, you have a summary file which can directly import it into Cytoscape, and which then maps the feature ID basically to the data from MCMine. But as I said, it's just a workaround we currently do because SIRIUS has its own feature ID, which is not exactly the same like MCMine, but it's just, we can just patch that both tools interconnect better with each other. Are there other questions? You have the summary files? Okay.